All right, let us begin. So, hope everybody had a good, relaxing weekend, or exciting, or both. Now back to the grind, right? So remember last time, way back in the last week before the weekend, we talked about this special class of Hurwitz numbers called double Hurwitz numbers. And what makes a Hurwitz number a double Hurwitz number is simply that the base curve has genus 0, is a P1, and there's exactly 2 points where you can prescribe your favorite ramification profile, and everywhere else you have to be simple, right? And these numbers are special in the sense that they do enjoy kind of combinatorial and algebraic properties that general Hurwitz numbers do not enjoy, and this has a reason in the symmetric group theory that we briefly touch upon. But the reason that we focus on double Hurwitz numbers is that there's a very natural tropical counterparts to double Hurwitz numbers called tropical Hurwitz numbers. And what we saw last time is that, the natural way that a tropical geometer likes to define tropical Hurwitz number is as the degree of a tropical branch morphism between a moduli space of tropical covers and a moduli space of tropical configuration of points in tropical P1, right? And so last Friday, Hannah also showed us how a tropical geometer computes such a degree by writing these gigantic matrices, right? And then noticing that the determinant is actually very simple to compute because these matrices are either lower triangular or block lower triangular or so on and so forth, right? And so then by doing this analysis, then you say, okay, I've written my gigantic matrix once in my lifetime, never again. You find out some sort of local combinatorial way of describing these determinants. And so this gave rise to a combinatorial algorithm to compute double Hurwitz numbers. And then there is a correspondence theorem that we'll talk about today that says that essentially tropical Hurwitz numbers are the same as classical Hurwitz numbers. Okay, so this is the summary. Any questions or comments? We're all good. So what I want to do today is sort of spend a little bit of time on these last 2 points. So let me first of all spell out the combinatorial algorithm in larger generality than last time, where I did just one example, right? So I'm going to define a monodromy graph. So a monodromy graph of type G X. And let me draw an example of one so that then as I write the definition is maybe going to make sense. Let me do this. And maybe this is going to be 4, 3, 1, 4, 2, 2, 1, 1. One, 2, 3, 4, 5. What is this? Okay, so this is going to be an example of a monodromy graph of type genus is 1, and the x is going to be 4 minus 1 minus 1 minus 1 minus 1. Okay, and let's see in general what these things are going to be, right? So it's going to be a trivalent tree of genus, by genus I mean first Betti number, G. Okay, so this is a tree that has exactly one loop, genus 1, so that's why the genus is 1, right? And then the edges, it's directed. Okay, so in this case, the left to right. Right, I'm thinking of. I may as well draw some little arrows, but if I think of gravity flowing from left to right, then I don't really need to do that. There's black hole. Okay, so gravity is definitely going that way. Oops. Strongly. It's pulling my flip-flops as well. What else do I want? So I want that the ends of this tree, so if you orient all ends inward, then they're labeled by the xi's, by the components of the vector x, right? So, I have a 4 for this edge that's oriented inward, and I drew 4 1s, which I drew only 2, but I should have drawn 4 1s for these ends. But you see, like with the gravity orientation, they're oriented outwards, and so if you actually flip the orientation, you flip the sign, so they should be minus 1s. It's not that important. What else do I want? I want a balancing condition. So the weights of incoming edges equal the weights of outgoing edges at all vertices. Did I even say that the edges should be weighted? Here, with weighted edges. Okay. And then the last condition is vertices have a total ordering compatible with gravity. Compatible with the direction of the edges. Okay? By this meaning that this ordering of the vertices, I've drawn it in green here with this first vertex, second vertex, third vertex, fourth and fifth, right? And the fact that it should be compatible with gravity means that I don't really have a choice for these 3 vertices. The first 3, this has to be the first one, because it's the one furthest away from the black hole. But 4 and 5, I actually had a choice, right? And it would be a different tree if I label them in a different way. Okay? And again, you can recognize that this is just a combinatorial description of these tropical covers, right? Because if I do have a map to the real line, well, then just ask the map which of these vertices is coming first, right? But now we've removed all the tropical geometry, and a graph theorist will be happy to talk to you if you show them this stuff, okay? Yeah, I'm saying that the total ordering is one of the datum of what makes a graph, a monodromy graph of genus GNX. Okay. Cool. And so now, like the algorithm, algorithm is that the tropical Hurwitz number is given by the summation over all monodromy graphs of type Gx of 1 over the order of the automorphism group of the graph gamma times the product of the weights of E, where E ranges over all internal edges. Okay. Okay, there's a question, yeah?
Is the automorphism of the graph, is that the underlying graph or with the weights?
It's the graph with all of the monodromy graph, so all the decorations. And in fact, I was trying to think whether I should shove this under the rug or not, but now that you've called me out, right? So again, depending on what kind of Hurwitz number, the way that we define Hurwitz number, I should also give labelings to the ends, right? One more set of 1, 2, 3, 4s, right? Especially if the ends have the same weight, right? Then they would be indistinguishable, so I want to distinguish. If instead you want to do like Hurwitz numbers, we don't label the ends, you get rid of this, and then, for example, this flipping these two forks, right, would be an automorphism. Right? So in this case, if I label the ends, then this graph has no automorphisms because I cannot flip these two edges right here because they have different weights, so that's not flippable. And I cannot flip these forks either because I've labeled the ends differently. But if I get rid of this decoration, then I can flip this two and I can flip this two. Notice I cannot flip the two big forks here because that would screw up the total ordering of the vertices. Okay, so yeah, so automorphism is always preserving whatever decorations you're giving graphs. Okay, cool. So last time we saw one example. Let me do another super fast example. E.g., let's compute the Hurwitz number. I think it's genus 0, but we'll see in a second. 3, 2, minus 4, minus 1. And this in R equals 2. Right, so I have to start from 3 and 2. I have two vertices to play with, so I can go to 5 and then 4 and 1. Or I can open this 3 into a 2 and a 1. This is a 2. I can join these two to a 4 and a 1. Or I can open the 2 and then I have my 3, 4, and a 1. Yeah?
The number of vertices, the number of vertices, is that prescribed?
It's not prescribed, but it follows from the Riemann-Hurwitz formula.
Yeah, but also in the algorithm?
I mean, I did not write it because this already determines the number of vertices to be 2g minus 3 plus n. And this follows from, again, if you're a geometer from the Riemann-Hurwitz formula, if you're a graph theorist from the other characteristic of a graph. Right? If you have a trivalent graph of a given Betti number and with a certain number of ends, then you can write down the other characteristic of this graph, and that will determine the number of vertices.
But also, over each point, if you project over each point, does that follow? Over each point, I have one vertex. I cannot have two vertices.
Yes, that's correct. You cannot have two vertices over each point. Yeah, and that comes from the fact that you're asking for a total ordering of the vertices, right? Because in a sense, I mean, I'm not telling you what the length of these edges are, right? So in a sense, it doesn't even quite make sense that to say over each point, because I don't have a map here. This is just combinatorics, right? But if you say, okay, if I want to think of the underlying tropical cover, right, then what we're doing is we're looking just at the top dimensional cones in this space of tropical covers, and those in particular will not have two, there will be tropical covers where this 4 and this 5 kind of lie on top of each other. That's a lower dimension, that's a face. And so we don't want to consider it. It's a face of a top dimensional cone. Okay. Great. Any other questions?
So for this algorithm,
Yeah.
I have a giant summation. Is there a way I can determine all monodromy graphs?
I mean, it's a finite problem, right? But I mean, I don't have a good answer for that in the sense that we didn't worry too much about what was the best way to make this efficient. The kind of things that we worried about is what kind of consequences we can get from this formula. We'll talk about that. But I mean, for small examples, I mean, for me, like the easiest way is just to build these graphs from left to right, right? You see at each vertex what are the possibilities, but that's kind of like it's an exponential process, right? Because every vertex you have a finite number of possibilities, and so it's big, yeah. Okay, so I don't know why this became 41. It's 41. All right, so I have my 3 monodromy graphs of type 3, 2, minus 4, minus 1. Right, and the weight of this one is 5. The weight of this one is 2. The weight of this one is 1. Right, and so the Hurwitz number is equal to, and none of this has any automorphism, so this is 5 plus 2 plus 1 equals 8. Okay? Okay, so yeah.
Just to check, there should be a 3 in the middle one, right?
Did I screw this up? Yes, I did. Thank you. 2 plus 1 is not. In fact, no, there should be a. No, sorry. This is right. Sorry. This is right, right? So 3 becomes 2 plus 1, but I have also 2 here, which is this one, 2 plus 2 plus 1. So what am I?
I think it's the same. I just didn't sort of to check my understanding.
Am I? Is something mislabeled though, or no? Okay, cool. Yeah, sorry. There's this 2 that went through it, right? And it looks like it was lost, right? Yeah, but it goes through. Okay. Now, obviously, you should slice this picture at any moment and see always the same degree, right? So that's the. Okay, but I mean, it's a really good point that if this algorithm was just an algorithm to compute numbers, it would not necessarily be a particular improvement with respect to understanding. Yeah, Angela.
Remind us why in like the second and third examples, we have to have a vertex between the repeated, like the weight and the end weight. Does that make sense? Like the internal edge has weight 1, and then we've got an external edge weight 1.
Mm-hmm.
Why do we need to have the duplication of the weight?
Oh,
Why do
like this and this? Yeah, you don't.
Okay.
This is just, I mean, again, this is,
It's an location I want.
for me, it's like, sometimes I repeat it here. It's psychological to remember that, okay, this is 3 plus 1 plus 1 is still 5, I'm good, right? But this 1 and this 3, right, once you've labeled this edge, you should know that this is the weight of the whole edge. Yeah, so absolutely. Absolutely. But let's like I said, what can you do with this algorithm? Well, Gould and Jackson and Vakil told us, well, you should not think of Hurwitz numbers one by one, right? They're double Hurwitz numbers are a happy family that come, you should think of the function, right? So in particular, I should not think of just this particular Hurwitz number. I should think of H0 r equals 2, x1, x2, x3, x4. Right? And so, well, what happens if we think of it this way, right? Well, first of all, you can say, okay, I'm just going to play the same game, but I'm going to start. Well, first of all, you need to decide, right? So how many of these xi's are positive, how many are negative? And so that's the very first thing that you need to decide, right? So let's see what are all the decisions that we need to make, right? So which and let's make some random choices just to see what happens, right? So for example, let's say x1 and x2 are positive, right? This is just e.g., it's not a definition, right? And so if that's the case, I need to start from x1 and x2, right? And then I have to create trivalent trees and get to x3 and x4. Okay? And I mean, certainly one thing I can always do is join x1 and x2. Right? And get to x1 plus x2. And then open up again, right, and get x3, x4. And because x3 plus x4 is equal to x1 plus x2, because these four things had to add up to 0, so yes, minus x3 minus x4 is equal to x1 plus x2. This is actually balanced. Right? So actually, let me put this is sort of an honest picture. Okay, so this picture, it always works, right? And notice one thing is that we started with the ends being labeled by variables, which in particular are linear homogeneous polynomials, right? And then the balancing condition is telling me that each internal edge gets weighted by sums of edges, so sums of linear homogeneous polynomials are linear homogeneous polynomials, right? So I mean, this is a silly example because again, I have only one edge, but you can play with longer example. In fact, you probably should or will this, in the afternoon, right? And every edge in the graph inside gets decorated by linear homogeneous polynomials, right? And so if you do things with variables, right, monodromy graphs that appear get decorated by linear homogeneous polynomials, and then you're taking as weight the product of the weights of internal edges. Every monodromy graph that contributes a linear homogeneous polynomial of degree equal to the number of internal edges. Okay, so we're starting to see the structure of the Gould and Jackson-Vakil theorem taking place, right? Okay, but at this point, maybe you should say, okay, well, then you have a finite number of monodromy graphs. Each monodromy graph has weight a polynomial. Why the hell isn't the Hurwitz number a polynomial? And where is the piecewise polynomiality happening? Okay, so to see where that start taking place, let's see, like, I mean, this is the lucky graph in this case that's always there. But let's see what else we can find as monodromy graphs for these problems, right? So like I said, we have to start with x1 and x2. Okay. I've already said, okay, I can create the first trivalent graph by joining, so I've used that. The other option is I can create a trivalent graph by sort of opening up things, right? And let's imagine for a second, right, that this x2 right here is very, very tiny, right? By which I mean much smaller than either x3 or x4. Actually, sorry, I didn't plan the reveal well enough. let me actually first say parallel what happened here, right? So the things that happen here, right, is either x1 opened, right, and then it opened into something that then became x3, and then this will become x4, right? And then this weight, I can write it as either x1 plus x3. Is that right? Yeah. Plus, because x3 is negative, right? Yeah. No, yeah, that's exactly what I was being confused, right? So this graph is actually this one. No. The other one. Which one is x1? x1 is 3. Okay, well, let's. So this is good because in a sense it's seeing what's failing, right? So this is a picture that kind of makes sense, right? Because I have an x1 coming here, an x3 coming in. So what I should have going out in this way should be x1 plus x3. But if we look at that example and I say, well, your x1 was 3, your x3 was minus 4, this would become minus 1, which is really not a legit graph, right? Which means that really the correct weight is minus x1 minus x3 for this graph. Okay, and maybe I should orient this way. I think I managed to confuse everybody, including myself. So let me try to, yeah.
Well, just, can you go why you changed the connecting chart? Because now it's connecting like x2 and x3, but it's x1 and x3 and the
Well, at this vertex, right, you still have an x1, an x3, and this other edge, right? They're all coming in, right? So their sum should be 0, right? And similarly, okay, so here's the thing, right? So let me erase this. So I have 2 more graphs, x1, x2, x3, x4, and I'm going to draw them like this. I'll draw them like this. In this case, x1, x2, x3, x4, x3. Right? So in principle, I have two possible graphs. For one where I have a vertex which is joining x1 and x3. The other one where I have a vertex joining x1 and x4. But here, right, I need to decide sort of what the weight of this edge is. And because weights at edges need to be positive, right, I could say that this is the absolute value of x1 plus x3, and this should be the absolute value of x1 plus x4. Right, and this is where the piecewise polynomiality happens, right? Because absolute values are not polynomials, they're piecewise polynomial functions. Okay, and so in particular, again, you see that in this particular example, I'm in a situation where, yes, for this graph, I have an x1 plus x3, and for the other graph, I have an x2 plus x4. Sorry, x1 plus x3, and I want x1 plus x4. Yeah, 3 minus 1. But this depends on sort of the, how big, the various entries are relative to each other, right? So let me actually make a qualitative statement. So let me make a definition. So a resonance hyperplane is a hyperplane with equation summation of the xi equals 0 for I in a subset of your index set. Okay, so in this case I have x1 plus x3 equals 0, x1 plus x4 equals 0, x1 plus x2 equals 0, x1 plus and x3 plus x4 equals 0. These are all examples of resonance hyperplanes, right? And in any connected component of the complement of the union of all resonance hyperplanes, then each monodromy graph has all internal edges weighted by the same linear homogeneous polynomial, which implies that the double Hurwitz number is polynomial. Period. Okay? And why? Because, well, if you are in a connected component of the complement of this hyperplane arrangement, that basically means that you've decided for every subset of the xi's whether that sum is positive or negative. And so you've decided for every possible linear form in the xi's whether you should take that linear form or negative that linear form to get the positive weight. Yes, Johnny? So on the resonant hyperplanes, we actually we don't talk about them, right? So
Like on the one on the left, like what happens if x1 is equal to negative x3?
yeah, so this graph will just contribute 0, right? And yeah, this graph will contribute 0.
So does it mean that the double corresponding factor is 0?
Well, no, just that the contribution of this graph is 0. Yeah. Yeah. Yeah, but it will be, it will have two different polynomial expression because you can use it, the polynomial expression from either chamber. And that, that graph will make it. Yeah.
When you like switch orthogs, switch the sides of the xi's, is it still like okay?
It's still okay. It's still okay. That's a really kind of a really cool kind of thing. So I'm trying to decide because I didn't want to spend the whole hour on this, but I can easily do that if I don't exercise a little bit of discipline. So let me just say a few things without writing anything more. And if you're particularly interested in what I'm saying now, let's talk about it in the afternoon or something, right? So this shows in a very simple way when the genus of the covers is 0, the piecewise polynomiality, right? Because really these are trees. Each tree has an edge decorated with linear homogeneous monomial. So, finite number of products of linear homogeneous monomials is polynomials, except when you change some of the signs of the sum of the excised first and subsets, and then you change some of the contribution of time on the graphs. So this also helps to compute to kind of compute the wall crossings, because when you change some of these signs and you want to see how the Hurwitz number changes, you can ignore all the graphs for which the contribution is the same on both sides. Right? So you can just focus on those graphs where the sign changes. Right? So for example, if I want to look at the wall x1 plus x3 equals 0, and say, how does the Hurwitz number change when you go from one side of this wall to the other side of this wall? Well, this graph, this tree, and this tree are unaffected. Because again, if you stay, if you're moving in a close enough neighborhood, you're not crossing any other wall. So the sign of x1 plus x2 and x1 plus x4 will remain unchanged. So these two contributions will be the same on either side of the wall, so they cancel when you subtract. And this contribution will appear with a positive sign on one side, with a negative sign on the other side. So in this particular case, across this wall, the wall crossing is simply 2 times x1 plus x3. And so in genus 0, again, it's easy to do this analysis in large generality and see that for any wall crossing, the wall crossing formula is given as the product of two other genus 0 Hurwitz numbers. Okay? In higher genus, things get a little bit more complicated because, well, one nice thing about genus 0 is that once you've decided the weights of the ends, then by balancing, you get the weights everywhere else. And so these linear homogeneous monomials are just determined once you draw a graph, right? Whereas in higher genus, I can draw the first example, which is this. There's not a unique way, right, to use the balancing condition to fill the edges, right? So here, I can choose, say, this to be I, and this to be x minus I, right? So I no longer have linear homogeneous monomials in x. I get affine linear monomials in x, or linear homogeneous in x and some additional variables, one for each genus, new genus. And then what do I have to do? You have to integrate over the integral values of, in this case, it's a segment, right? You have to integrate from I going from 1 to x minus 1, or 1 to x, it doesn't matter, or 0 to x. Okay? And in general, for genus G, you'll have to sum this contribution of the integral lattice points of a G-dimensional polytope. Okay, again, by Calc 1 arguments, discretized, also called error theory or lattice count theory, right? If you have a polynomial again a degree and you integrate over the lattice points of a polytope of a given dimension, you get a polynomial of degree equal the previous degree plus the dimension. So it's still easy to see that you get the right kind of degree. The wall crossings get a little bit more difficult to control, because then you observe that the wall crossings happen when the topology of this polytope changes, and there's a lot of fun to be had, but not now. Okay? Yeah?
So the statement of that theorem holds also in genus B, isn't it?
The statement of the theorem holds for every genera. Yeah.
The problem is the word crossing.
I mean, there's no problem. Is that like in genus 0, again, if I wanted to devote this whole lecture to wall crossing with genus 0, I could actually like give a reasonably like self-contained explanation of everything that happens in genus 0. In higher genus, well, for one thing, I couldn't just wing it. And for the other thing, there's quite a bit more of sort of convex geometry and algebraic combinatorics that goes into it, but it's doable, right? And again, even in higher genus, the wall crossings are expressed as products of smaller Hurwitz numbers, no longer just a simple product of two of them. There's some sort of like you write some big formula, which is pretty or awful depending on your point of view. Questions, comments? Like I said, this is more like a sketch, because in my mind I didn't even want to talk about this, but I got sidetracked. But I'm totally happy to talk more in the afternoon. Okay, what I wanted to spend a little bit more time today is mention why the correspondence works, right? So this is sort of like we have a combinatorial algorithm. This combinatorial algorithm somehow connects double Hurwitz numbers to sort of this algebraic combinatorics that allows us to say things about double Hurwitz numbers. But why are we actually saying things about honest double Hurwitz numbers? Well, there's a couple different ways to see this. And let me y h g x drop is equal to h g x. Okay, so the first perspective is through cut and join. So cut and join is a statement about the symmetric group. Okay, so is the following statement is that if sigma is a permutation in SD of cycle type eta, and tau is a simple transposition, then the cycle type of the product sigma times tau cannot be too different from the cycle type of sigma. Okay? It's a simple exercise that to see that you can only two things can happen, right? Either you can join two cycles of sigma. You can see that instead of an m and an n cycle of sigma, you get an m plus n cycle. Or you can split a cycle of sigma. So instead of an m cycle, you end up with an m1 and an m2 cycles. Okay? And this is sort of represented graphically, sort of this way. So the join is and the cut is represented by this. So you can join two cycles, or you can cut one cycle. Okay? And in fact, the cut and join equation also tells you, and again, this is I think it's one of the exercises I put in the homework, and it's fun to do it. The cut and join equation tells you if you have a fixed permutation sigma and you run over all possible transposition taus, how many times you're going to join a cycle and how many times you're going to split a cycle. Right? And this is happening m times n times. For the join, and n times for the cut, unless if m1 is different from m2, and this becomes n divided by 2 if m1 is equal to m2. Okay, so if you've never seen this before, please for now just believe me that, if we spend 10 minutes together this afternoon with the exercise and I give you a couple hints, you will actually be able to see why this is the case. But I told you I was going to tell you why the correspondence theorem, and instead I told you some seemingly random fact about the symmetric group, right? But this random fact then got assigned to some trivalent vertices with some weights that satisfy the balancing conditions, so maybe I'm not totally misleading you, right? So let's remember, one way to count, so double Hurwitz numbers, can be computed by counting monodromy representations. And in this specific case, right, this is the same as counting R plus 2 tuples of elements of the symmetric group. Let me call them sigma 0, tau 1, ... tau r, sigma infinity, right? Such that the taus are simple transpositions, and sigma 0 and sigma infinity have prescribed cycle type. And we really want to count all possible ways of choosing this data. Okay? And so, again, this is a big, nasty count. right? But one way that I could organize this count is by what is the cycle type of all consecutive products, right? For each one of these data, what I could collect is the cycle type of, so I want to organize this count by the cycle types of the products sigma 0, sigma 0 tau 1, sigma 0 tau 1 tau 2, all the way to, tau r, tau 1, sigma 0, and then sigma infinity, tau r, tau 1, sigma 0. Okay? And some of these things I know, right, because this is the identity. Always, so I don't really need to worry about this. This is sigma infinity inverse. Always, so I also don't really need to worry about this. But now I say, okay, what is one way to keep track? First of all, what happens between here and here? I'm multiplying by transposition. Right? So I have a list of cycle types of, where the consecutive entries differ by having multiplied by transposition. So one way that I can graphically organize this thing is by doing the cut and join analysis. So I always have to start with cycle type sigma 0, cycle type equal to the cycle type of 0, 0. So I can start by drawing x0, 1, x0, and 1, like n strings, right? And then after I multiply with the first transposition, I'm going to draw the corresponding trivalent vertex depending of whether I've split a cycle or joined some cycle. And so you see that this graphical way of like keeping track of all the possibilities here gives rise to precisely monodromic graphs. Every time I hit with a transposition, I get a trivalent vertex. And then, okay, at that point, you just have to do the analysis of what the multiplicity that the cut and join equation tells you, and then you will see that this multiplicity agrees with that statement, and that's a proof. Then this was the original proof of the correspondence theorem. So again, I'm going quite fast on the details, but I hope that's for the best. Any questions, anything which is not at least qualitatively clear? Yeah, Alessio.
This does not explain why this is equal to the degree of the branch map, the tropical branch map, right?
No. So there's one theorem which is entirely in the tropical world, right? Which is saying why the degree of the tropical branch map is that algorithm, right? Now, what this is saying is why is that algorithm the same as the classical Hurwitz number by going through the correspondence with the monodromy representations. Okay? So of course, you could say, well, I would be more intellectually fulfilled if I had some sort of proof that connects directly the classical and the tropical branch morphism. Right? And that's where we're headed. Right? That's, yeah. Cool. Any other questions? Okay, cool. So let me clean up, see how much time I have. And do I stop at 45? So I have 3 minutes? Okay. Is everybody really hungry? Because, All right, let me just give a preview then, not actually get into it yet. So geometric approach that motivates, that explains the correspondence theorem goes through the degeneration formulas. Okay, so this idea is to see that compute the degree of the algebraic branch morphism, let's say alg, by choosing a point in a zero-dimensional stratum of the space of branch divisors. And then this is a contribution. This gives rise to a bijection with monodromy graphs. Okay. But then each of these zero-dimensional loci in our moduli space of covers needs to be counted because of some stacky nonsense with some multiplicity. And then one checks that the multiplicity that you need to count it with is precisely the same as those determinants of those matrices that Hannah was writing down. And so that gives you like a more direct kind of proof of concept of this correspondence theorem. So that's what we'll spell out, hopefully more clearly next time. And I'm going to stop early then. No, I'm stopping on time. Question? Yeah.
So are you saying that like the branch morphism is flat?
Am I what? Sorry?
Saying the branch morphism is flat?
So in the case of the admissible cover compactification, yes. In the case of the relative stable map compactification, it's virtually flat. It's good enough, right? But yeah. Yeah. Yeah, I'm going to choose a very specific degeneration, and that choice is the one that gives rise to a bijection with monodromy graphs. Yeah, absolutely. Cool. Let's go eat.